Okay, this is Jared Gavin. I'm your instructor for college algebra. I will be covering the sections of our college algebra workbook through video. Hopefully, these videos will help you to keep up in class since we usually don't go backwards. We pretty much cover new material every day. Or perhaps you could use them to review some of the things we've already covered. So, going to get started. Section 1.1 functions. Okay. A function basically consists of a rule, and it takes an element from one set to a second set. You could say that it maps an element to another element. Okay, there's a lot of names that we could refer to the first set by. We can call it the first set. We can call it the input. We can call it the domain. All right, and then there's the second set. Okay, if you'll notice, we have some examples of functions here, and specifically these are arrow diagrams, and you'll see that we have two ovals. Okay, they represent our two sets. So the first one is our first set, our input, and then the second one, we can refer to it as our output, or we can refer to it as the range, um, or we can refer to it as the image. Okay, so a function is a little bit more specific than just assigning a first element to a second element. Okay, in that each first element assigned only goes to one element in the range. Okay, the second set. So we have two examples here that are functions, and then we have one in the middle that is not a function. Okay, and our elements can be anything. In this case, they're dots. You can have elements such as shapes, colors, but mostly in algebra, this class, college algebra, we'll be dealing with elements, numbers, okay, real numbers. So in this case, you look at the first oval, this first function, each dot, and we've got four dots, each dot has an arrow going away from it to a dot in the second oval. Okay, and each dot in the first oval only has one arrow going away from it, so it is a function. And the same case with the last arrow diagram, every dot in the oval, and this one's different. We have more dots. This one has five. The first one has four. Okay, so each of the five only has one arrow leading away from it, and so it's only assigned to one dot in the second set. And you also notice that the second, third, and the fifth dot are assigned to the same dot in the second set. And that's okay. It doesn't violate our rule for a function. Now, the middle arrow diagram obviously has the first dot assigned to two different dots in the second oval. Okay, so this violates our definition of a function, so we label it as not a function. We could call this middle arrow diagram a relation. Also, one other thing I didn't mention about the third arrow diagram is that some of the dots in the second oval have not been assigned to. Okay, and that's okay. If you'll look down at the bottom at example 1, they are giving us a first set, which, like I said, most of the time we'll be dealing with what we consider to be algebraic equations, a different representation of a function, which not every algebraic equation is a function. But down at the bottom, we call the input, we label it as the X set, and we have Camry, Corolla, Accord, Civic, Cobalt, and Impala. So they want us to fill out these arrow, or this arrow diagram. We have this shape on the left. It'll be our input. I can label it as such, and then the other one would be our output. Okay. And we don't know whether this is going to be a function or not. Okay, so I'll put my elements in my first set using the abbreviations Camry, CA, Corolla, CO, Accord, AC, Civic, CI, okay, Cobalt, CO, and Impala, IM. Alright, our second set, Y, our output, okay, would be the makes of the cars: Toyota, T, Honda, H, and Chevy, C. Okay. Directions say use your common knowledge to establish a correspondence. Alright, we're going to take the model and we're going to map it to the make with arrows. So a Camry's a Toyota, so I map it to T, and a Corolla is also a Toyota. Accord is a Honda, and Civic is also a Honda. Cobalt is a Chevy, and Impala is a Chevy. So the question is, does this represent a function? And the answer would be yes. This is a function. Okay. Why? Because every element in the first set is assigned to an element in the second set, and every element in the first set has only one arrow leading away from it. It's only assigned to one element in the second set, so it is a function. Okay, page 2. We have another input and output set. We want to arrange those in this arrow diagram. Okay, and then we want to decide if it's a function or not. So input set X is Joe, Alan, and Bob. Y, our range, our second set is algebra, ALG, biology, sociology, and English. Okay. Now it tells us how to make the assignments. It says Joe is taking algebra and English. So I'll draw arrows from Joe to these two classes, and right away we violate the definition of a function. We can call this arrow diagram a relation, but with Joe going to two elements in the second set, not a function. So not a function. Alright, so I'll just go about drawing the rest of our arrows. Alan is assigned to sociology. That's the only class he's taken. And Bob is assigned to biology, and then he's also taken English. So Bob also is assigned to two different outputs. So between Joe and Bob, we definitely don't have a function. It only takes one, though, to violate the definition of a function. Alright, let me erase this. And we'll move on to the next example. C, okay. It says, which of the following tables, F and G, and that was another way we could represent a relation or a function through a table. For the one which is a function, determine the domain and the range. Okay, let's take a look at F. We see that we have an input 0 and 3. Okay, 0 is assigned to 3. 2 is assigned to 4. 4 is assigned to 7, and so on. Okay, if you look over here, we don't have anything assigned to a 6 here. Okay, and that's okay. That doesn't violate our definition of a function. We're only worried about the input, so basically what we're looking for is an input that repeats. Okay, and so you look through your list of inputs and we see these two. Okay, 2 and then another 2, and obviously they're assigned to 2 different outputs. 2 is assigned to 4 and also 2 is assigned to 13. So this F is not a function. F is not a function. Okay, we could list the reason. 2 has 2 different outputs. Okay. Alright, what about G? Well, if you look down through the inputs for G, 1, 3, 7, 12, 14, 22, 24, and 30. Okay. They always increase, so we never repeat. We don't repeat any of these inputs. Okay. Let's see if any of the outputs repeat. This wouldn't violate our definition of a function, but let's see, 58, 55, 52. Okay, not that I see any of the outputs repeat. Okay, just checking. Even if one of the outputs repeated for one of the inputs, that would be fine, as long as we don't have a repeat of an input. So G is a function. G is a function. Okay. And the instruction told us that we wanted to list the domain and range. So D of G, okay, D for domain, subscript G for the particular relation that we're talking about. In this case, G is a function. So if we want to write out the set of the domain, we would write 1, comma, 3, comma, 7, 12. Hopefully I won't run out of room here. 14, 22. Okay, I can write over there. Erase that. 22, 24, comma, 30. And we would close our set with a bracket. Okay. Not the best bracket, but these are all the numbers in the input, so we would call them the domain since G is a function. Okay. I'm going to have to make some room. I'll go back and erase this stuff about F. I got some of the domain here. Sorry about that. Okay, the range, R, and G. Let's write out this set. We've got 58. Let me scoot this over. Okay, I'll try to do better in the future. Okay, R, G. S bracket again, but 58, 55, 52, 57, 68, 7, well, oh, 68, 79, negative 31, 71. Okay. Now, in this case, we use the term range somewhat loosely. I like to call the range the list of the outputs that have been assigned. So 58, 55, 52, all these other numbers. Notice that 54 and 70 weren't assigned. You can, some people call this the range. Other people, more specific, call it the codomain. Okay, I like to use the range in the context of only the numbers in the output set that were actually assigned. Okay, let me erase this stuff and we'll move on to the next example. Okay, these are, we know they're relations because we have an input assigned to an output. But which ones are functions? And this one is communicated through sets of ordered pairs. Alright, so we've got relations F, K, H, and G. Let's just simply check the inputs. Okay, ordered pair, we just have inputs input first, like the X and the Y, output second. Okay, just to show you the format. And so for input, input, I've got 2, 3, negative 1, 4, negative 3. Notice how none of the inputs repeated. And so F would be a function. Okay, is a function. What about K? Okay, let's look at our inputs. Negative 3, 2, 0, negative 3, again. Inputs. Negative 3 repeats. Okay, so K is not a function. Negative 3 is assigned to negative 2, but then negative 3 is also assigned to 1. So K is not a function. Not a function. Okay, what about H? Again, we look at the inputs. We have 3, 4, 0, 7, and 4 again. So we have 2 inputs, 2 inputs, repeat. Okay, not a function. What about G? Inputs 2, 3, negative 1, and 4. None of them repeat, so G is a function. So we're looking at page 3. Okay, and we've seen functions representative sets of ordered pairs. We've seen arrow diagrams, and now we're going to talk about functions as algebraic equations. It's actually quite simple to identify some of these. Two important things that you need to realize is basically about radicals. Okay. When we solve for y, the output, we don't want to get two equations that if we got two equations that would give us two different values for an output for one particular input. Okay, so we have these two reminders here. U squared equals a. Okay, remember it has two solutions because of the square root property. But then if we have an equation u to the third equals a, we only have one solution. Okay, so let's say we had an equation y squared equal x, just to remind you of the square root property. Then we would take the square root of both sides. Square root is the opposite operation of squaring something, but then there's the catch. Okay, when we take the square root of the left side, okay, the square root of a radicand that has a variable in it, sometimes we need the absolute value bars, okay, and in this case the exponent is even, okay, and it matches the root number 2, and so what we would say is we want our result from the square root of y squared to be positive. Okay, so we need the absolute value bars. On the right side we have square root of x. Okay, with these absolute value bars we say that, well, we have two options for y. We could say this is, in other words, if we put in square root of x, we would get square root of x. Okay, absolute value of a positive square root would give us a positive square root of x. And then if we put in a negative square root of x, we would get the right side again, positive square root of x. And so this absolute value just causes us to have to take y, and y is a result of square root of y squared, and when we take the square root of the right hand side, we have to put a plus or minus in front of the radical to account for these two possibilities. Okay, that doesn't happen with the cube root. So, real simple, let's just look at these equations, and if we pick out an equation and we look at the y and it has an odd exponent, then it is a function. In this case we've got 2x minus y equals 7. I could solve for y minus 2x both sides. Negative y equals minus 2x plus 7, and then my y is negative, so to fix that I could simply run through the entire equation and switch my signs. So we solve for y and we only have one equation, y equals 2x minus 7. We can call this a function. B, this is not a function. look at the y variable, it has a 2 for an exponent, and that would also apply to any equation where y has an even exponent. So in this case, if we try to solve for y, we would subtract x from both sides. We'd have y squared equals minus x plus 16. Then we would take the square root, okay, and we'd have to put in plus or minus here. So on the left, we could say that we get a y, but then on the right side, we would get plus or minus 16 minus x. And you need to see this as two different equations. We have y equals plus square root of 16 minus x. And we have y equals minus 16, or square root of 16 minus x. Okay. For one x, we have two y's. For one input, x, we have two outputs, y. So, not a function. Okay, now that you have an idea as to how you identify an algebraic equation that is a function and why, we'll just simply run through the rest of them. There's this one, and then there's a couple on the next page. Look at y. The exponent is understood to be a 1, and 1 is odd. So this is a function, is a function. Okay, page 4, D. We look at the y variable in the equation, and it has an odd exponent. So when we solve for y, we would only get one equation. So this is a function. Okay, and then E. You notice that we have for y even exponent. So when we solve for y, we get 2. We get a plus equation and a minus equation, so to speak. This is not a function. Okay, example 3, probably something you've seen before if you took intermediate before this class. We have function notation, f of negative 2. This is not f times negative 2. We're given the algebraic expression for f. Okay, these are basically our instructions telling us what to do to x to get the output. So we take this expression and we leave out the x. Okay, this dot is just a result of me using a pen tablet. I don't know how to stop that at the moment. But this is where x was. X was squared, and then we add 3. Instead of putting an x in there, I put a negative 2. If we square a negative 2, negative times negative is a positive, so I get a 4. Pick up the plus 3 on the side, and f of negative 2 is 7. Okay. F of 5. F is the same algebraic expression. We square x and then we add 3. So inside here I would put a 5. 5 squared is 25 plus 3, I'd get a 28. So f of 5 equals 28. We could write out the ordered pair for the input output, and that would be 5 for x and 28 for y. Okay, f of 2.7, we would take 2.7, square it, and add 3 to it. Okay, let me calculate 2.7 squared. Here's my calculator, TI. Let's see if I can move this around. All that writing. Turn it on. 2.7 squared. Enter. 7.29. So 7.29 plus 3, and we get 10.29 as our output. As an ordered pair, we would write 2.7 for x and 10.29 for y. Now we have a fraction that we want to input into our expression, x squared plus 3. So I have a 3/5 inside. Okay, square both the top and the bottom. I would get a 9 over 25 plus 3. If we want an exact answer, then we need to change the denominator. We need a common denominator. So I will use 25 for both fractions. This would still be a 9, and then this 3 had a 1 as a denominator. So I need to multiply both the top and the bottom by 25. This would be a 75. We add the numerators, we would get an 84 over 25. Of course, you could probably calculate that with your calculator. More than likely, you'd end up with a decimal. Let's see. Okay, I'll bring up my calculator back up. I want to show you how you can take a decimal with TI-89, change it to a fraction. So we'll go back to f of 3/5. Okay, 3 over divide by 5. I want to square that. Okay, and then I want to add 3. Enter. Okay. This really wouldn't be too bad to convert back to a fraction. Looks like it's a terminating decimal, but one thing we can do with the TI-89 is go to the math menu and call this operation fraction. Okay, notice that it pulls this answer above it down, ANS, answer, and now it's going to convert it to a fraction. Enter, and we get 84 over 25. Okay, so last example on this page, consider the functions f, g, and h, and they show us the operations that we carry out on the input x. Okay, it wants us to compute f of 1 plus 2 times h of 3. You have to recognize these you have to recognize this f and this h of 3 as function notation. Okay, and it gives us a hint. We want to calculate these separately. So we'll calculate f of 1, we'll put it back in the expression. We'll calculate h of 3, and we'll put it back in the expression and multiply it by 2. Okay, f is a negative 2 x plus 4. Okay, we want to take the x and we want to replace it with the 1. So negative 2 times 1. We get a negative 2 plus 4. 4 minus 2, 2. H, we have this expression. We have a square root. Okay. 3 times 3 plus 7. And that radical extends over that whole 3 times 3 plus 7. Alright, 3 times 3 is 9 plus 7. We get the square root of 16. And we say that's 4. Okay. So we got our f, we got our h. F of 1 plus 2 times, oh, let me write this out the way they have it written above, h of 3. So f of 1 is 2. We replace that whole function notation with a 2. Then 2 is a part of our expression, and then all of h of 3, this whole notation gets replaced by 4. And so now we just apply the order of operations. 2 plus 2 times 4 is 8, and 2 plus 8 is 10. Okay, page 5, we have a different expression. We're still referring to the same f from the previous page. And now we're not only putting a number inside of f, but we have an expression that contains a variable. Okay, and we also had a function on the previous page that was called h. Notice that these h's do not have or are not followed by a set of parentheses, so this is not function notation. H in this case is only a variable. Okay, f of 3 plus h is not the same thing as f of 3 plus h of x. Okay, these are different. This h is a variable. This is referring to the function. So we'll follow the same procedure as we did in the last example, and we'll calculate these two pieces of the expression first. 3 plus h, we want to insert that into f. Okay, so f was a negative 2 times x plus 4. So inside of here I would put a 3 plus h. If I distribute my negative 2 throughout my parentheses, I would get a negative 6, negative 2 times 3, negative 6, and a negative 2 times the h is a negative 2h. And then I just pick up my 4 on the outside. With this expression I can combine like terms. A negative 6 plus a 4 would give me a minus 2. F of 3, negative 2 times 3 plus 4. Again, I get a negative 6, but there's no h, so I just add a 4, and I get a negative 2. Okay, now we're going to take this expression and replace the function notations with the results that we had. Okay, f of 3 plus h minus f of 3 over h. We can strike out this whole notation here. We know what f of 3 plus h is. It's minus 2h minus 2. Then this minus is a part of the expression, so we bring it over, and then f of 3 alone is also negative 2, so we get a double negative here. This negative is from this output. This negative is from this expression. Carry the h over to the denominator. This is minus a minus 2, so this would become a plus sign, and we have a negative 2 plus a positive 2. So these two 2's would cancel each other out. We'd have a negative 2h divided by an h. The h's would cancel, and we'd be left with just a negative 2. Okay, sort of switching gears. C says find the real values of x such that g of x equals 0. Okay, notice that g of x equals 0 is not the same as g of 0. Okay, we're going to do something different with the 0. Have to go back to the previous page and figure out what g is. Okay, so g is x squared minus 3x plus 2. Okay, this is g of x. Okay, this is telling us g of x should be set equal to 0. So I'm going to take this polynomial and just simply set it to 0. And now we have a quadratic equation. Okay, it's already set up in standard form. So this piece, all we have to do is factor it. And hopefully it's factorable. We're basically doing the reverse of the full method. So these first, this factor is going to be a binomial. This second factor, or the second set of parentheses, is going to be a binomial. And we're going to write x here and here. Okay, if we were to apply the full method, we would say x times x, and we'd get this x squared term. Now we need to come up with our numbers. These numbers here and here to complete our binomials. Those two numbers need to multiply to give me a plus 2, and they need to combine to give me a negative 3. And a negative multiplied by a negative will still give me a plus 2. So negative 1 times negative 2 is plus 2. If I add negative 1 and negative 2, I get the b, the negative 3. So this is a perfectly good way to factor that polynomial. Now that we have this polynomial separated into factors, we can break this equation up into two easier equations. We have x minus 1 equals 0 and x minus 2 equals 0. Okay, this is something that you should have picked up in intermediate. If I solve these two separately, I would get the result x equals 1 and x equals 2. Okay, x equals 1 because I add 1 to both sides of this equation, and I get that. Okay, so you could look at these two numbers two different ways. You could call them the zeros of g of x, or you could call them the x-intercepts of g of x. Okay, D is wanting us to do something different. It's wanting us to find values of x so that these two functions are equal, or they result in the same output, f equals g, and we'll just do exactly that. F was a negative 2x plus 4. Okay, so I just put negative 2x plus 4 on the same side, the left side, And g from the previous problem was x squared minus 3x plus 2. Okay, if you scan through the equation and you see this x squared term, that usually means that you're dealing with a quadratic equation. And in that case, we want to put it in standard form, meaning that we want to move all of the terms to one side and we want to be left with 0 on the opposite side, much like this equation that we solved in the previous example. So, look at this equation. I see my x squared term is positive. That's the way that I usually factor polynomials. And we're going to have to factor since it's quadratic. So I'm going to take these terms on the left and move them to the right. So to move the 2x, I need to add it. And I'll just line up the 2x under its like term on the right. And I need to subtract 4 from both sides, and I'll line that up under the 2. These terms cancel out, and I'm left with the 0 on the left side. I still have my x squared, and negative 3 plus 2 is negative x. Plus 2, or a positive 2, and a minus 4 would give me a negative 2. Okay. We take this piece as polynomial, and I'm just going to write it out to the side. I'm going to factor it. Like the last one, we need x for our first term of each binomial. X times x would give us this x squared. And I have a negative 2 here. So I want my numbers that I insert in these parentheses to multiply to give me a negative 2 and add to give me a negative 1 in the middle. I'm going to go with negative 2 and plus 1. Negative 2 times 1 is negative 2. Negative 2 plus 1 is negative 1. So this is how we factor that polynomial. And now I would take these and write separate equations. X minus 2 equals 0. And x plus 1 equals 0. Okay. One-step equations. If I solve x minus 2 equals 0, I get x equals 2. If I solve x plus 1 equals 0, I would get x equals negative 1. These are not zeros like the last one. These are just the x values such that the output of f and g are equal. Okay, piecewise functions. You can see that for both f and g, we're given two different expressions. Okay, but like we said for a function, and we are calling it a function, we only want one output per input. So what we've done is we've assigned this expression to only a part of the inputs, and the other half of the inputs this expression. So we don't actually get 2 for every x. Okay. So working with this first one, f of x, we have a negative 2. We have to pay attention to our input. Looking at negative 2, we have to decide which inequality negative 2 satisfies. Okay, negative 2, this first inequality, is it less than a negative 1? And this is true. Okay, since the first inequality is true, we would use x squared minus 1 to calculate f of negative 2. So f of negative 2 equals negative 2 squared minus 1. Negative 2 squared is 4, minus 1 gives us 3. Okay. we would not use 2x plus 1 to calculate f of negative 2. Okay. Again, f. We're dealing with this piecewise function f. Check our input. It's negative 1. Which inequality does it satisfy? Okay. And again, it satisfies the first one. Okay. Negative 1 is not less than negative 1, but it is equal to, and that's what this bar indicates. So negative 1 is equal to negative 1, and we would use this first expression, x squared minus 1. Okay, so f of negative 1 equals negative 1 squared minus 1. We square negative 1, we get a positive 1, we subtract 1, and we get 0. Okay. What about f of 0? Well, we're back to this piecewise function. Which inequality does 0 satisfy? 0 less than or equal to negative 1. False. 0 greater than negative 1. True. So we would use 2x plus 1 to calculate f of 0. Okay, f of 0 equals 2 times 0 plus 1. Okay, 2 times 0 is 0, so that knocks out the 2, and we just end up with 1 for f of 0. Okay, what about f of 3? Well, 3, like 0, is greater than negative 1. True. So f of 3 equals 2 times 3 plus 1. 2 times 3 is 6, plus 1, 7. F of 3 is 7. Okay, G, new function. Okay, we're focusing on these two expressions, and we have a different reference number for our inequalities, 0. Okay, so is negative 2 less than 0, or is it greater than 0? Negative 2 is less than 0. So G of negative 2 equals, we go with the first expression, 2x minus 1. So we have 2, our x is negative 2, and then we subtract 1. Negative 2 times a positive 2 is negative 4, minus 1, negative 5. G of negative 2 is negative 5. G of 0. 0 less than 0. False. 0 is equal to 0, but we do not have the dash below the less than sign. Okay, so we go with the second expression, negative 3x plus 5, greater than, equal to 0. Yes, it is equal. True. So G of 0 equals negative 3 times 0 plus 5. 0 knocks out the negative 3, and we get 5 for G of 0. G of 2. 2 is greater than 0. It's positive. So this would simply be 3 times 2, or negative 3 times 2 plus 5. Negative 6 plus 5 equals negative 1. G of 2 is negative 1. G of 4. 4 is also greater than 0, so we go with negative 3x plus 5 expression to calculate g of 4. Oh, there's another dot. So negative 3 times 4 plus 5, negative 12 plus 5, negative 7. Okay, page 6, we're still talking about section 1 of chapter 1. And now we're shifting gears to a different question. What is the domain of a function? So, as I mentioned in class, two of the more difficult questions that pop up in this first section would probably be whether an expression or a relation is a function or not, and mostly in regards to an algebraic expression, which it turns out to be simple to answer. If y has an even exponent in the algebraic expression or equation, then it's not a function because of the square root property. But then if y has an odd exponent, it is a function. Okay, different question now. This is probably the second most difficult. What is the domain of a particular function? Okay, and whenever you're asked that question, it would probably be easier to answer the converse of that. What values are not in the domain? Okay, and we look at 4 different situations on this page. The first one, v equals 4/3 pi r to the third. They tell us that this is the formula for the volume of a sphere. Now, if I were to simply give you an equation, y equals 4/3 pi x to the third, and I didn't tell you that y and x had any significance. They didn't represent anything real world. They were just variables that represented real numbers. Then for this particular equation, we would say the domain would equal, I'm just trying to write a set. I want to do interval notation. The domain would be all real numbers. Okay. And let me see. Again, x and y, you're not told they represent anything other than just real numbers. Okay, but that's not the formula that they gave us, or the equation. They gave us a v and they gave us an r. Difference being v represents volume and r represents radius. These are real world quantities, and we don't measure those things using negative numbers. So for this particular formula, we would say that the domain, and I'll just use the domain of v, our volume function, is equal to 0. I suppose a shape can have a 0 volume, or instead we could put a 0 in for r, a 0 radius, 0 to infinity. Okay, we do not want to put negative values in for r, so this would be our domain. Okay, so pay attention to formulas that have physical quantities. Okay, what about a? Well, right off the bat, you notice something special about f. It has a square root. Okay, a important fact about square roots is that we don't want the radicand, the 2x minus 1, we don't want that to be negative. Okay, and it could possibly be negative depending on what x is. So square root of a negative gives us a complex number that is not real. Okay, so for the domain of f, we want only values of x such that 2x minus 1 is greater than or equal to 0. Okay, so to find the domain, we actually figure out what's not in the domain. We solve this inequality, add 1 to both sides. We get 2x is greater than or equal to 1, and then we divide by 2, and we see that x is greater than or equal to 1/2. Okay, to write that domain of f, we use a bracket because we have the equal sign, 1/2, and anything greater than that or out to infinity would be included in the domain. If we put any of these numbers into f, we'll get a real number back. Okay, so this is one special case that you need to look out for. A square root or a fourth or a sixth root can restrict the domain of your function. So what about h? Okay, important thing to notice about h is that we have x in the denominator. Okay, that could lead to us dividing by 0, and that's another thing that we don't want. So, for h, we say x minus 1 does not equal 0. If we solve this for x plus 1, x does not equal 1. So, if we don't want x minus 1 to be 0, then we can't let x be 1. So, the domain of h would be from negative infinity to 1, exclude 1 with parentheses. We would sort of jump over 1 with the union symbol, pick it back immediately after 1, and carry on out to infinity. So basically what we're saying is any number will work for h of x except 1. Okay, R. Well, it turns out R's domain isn't restricted. If you look at R, we don't have an x in the denominator, and we also don't have any radicals contained in the expression for R. Okay, so in general, if you look at your polynomial, your function, or supposed function, and you check your variables and you notice that all of the exponents are positive and whole. So our exponents of our variables are positive and whole, then in that case we can say R. Okay, hold on. The domain of R is all real numbers. Okay, so again, we didn't have any of these two situations. X were just numbers. They don't hold any real world physical quantity significance. And we have positive whole numbers for exponents of the variables. So the domain is all real numbers. We can put any number that we want to into R for x, and we'll get a real number back. Okay, so these are some exercises that you could do on your own to sort of test what you learned from this section, but this does conclude section 1 of chapter 1.